around us is built from familiar substances, like steel and glass, but tucked away in strange laboratories are materials with properties that seem almost impossible. For today's video, we're going to take a look at 15 of the weirdest known materials. Let's start with number 15, Vantablack. Vantablack is one of the darkest artificial substances ever created, and it's fascinated scientists, artists, and the public since its development. Its name stands for vertically aligned nanotube arrays, and that description gives you a clue as to what makes it so strange. Vantablack is made from a forest of microscopic carbon nanotubes that are tightly aligned vertically. When light hits the surface, instead of bouncing back, the light becomes trapped within this forest, bouncing around until it's absorbed. The result is a material that reflects almost no light. It absorbs up to 99.965% of visible light, making it appear so dark that three-dimensional objects coated with it look like flat, featureless voids. The effect is kind of unsettling because our eyes rely on reflected light to perceive shape and texture. Looking at something covered in it is like staring into a hole in space, even if the object is right in front of you. The material was first developed in 2014 by Surrey Nanosystems in the United Kingdom, primarily for aerospace and scientific applications. Its ability to absorb stray light makes it useful for telescopes, cameras, and sensors, where eliminating unwanted reflections improves its accuracy. For example, Vantablack might be used inside optical instruments to prevent internal light scatter that might interfere with sensitive measurements. The material has also attracted some attention outside of science. Artists and designers were intrigued by its visual effect, but its use was restricted due to licensing agreements. The British artist Anish Kapoor gained exclusive rights to use Vantablack in art, sparking a bit of controversy among other artists who felt that such a unique material should be more widely available. This led to the creation of alternative superblack materials by other researchers, some of which rival or surpass Vantablack's darkness. Despite the hype, though, it does have limitations. It's not a paint or a pigment in the traditional sense, but rather a coating that requires a specialized process to apply. It also can't withstand any abrasion, as the delicate nanotube structures are easily damaged. For this reason, it's remained mostly scientific and industrial in use. But the strangest aspect of this is how it sort of challenges our sense of perception. Humans rely heavily on vision. Seeing an object disappear into blackness is disorienting. It shows us how profoundly material can manipulate light, and it reminds us that our visual experience is not absolute, but dependent on the interaction of light and matter. In a world filled with bright colors and reflective surfaces, Vantablack stands out precisely because it doesn't, leaving behind what looks like nothing at all. Number 14, Aerogel. Aerogel is often described as the world's lightest solid material, and for good reason. Sometimes nicknamed frozen smoke or solid air, it's a synthetic porous material created by replacing the liquid component of a gel with a gas. What remains is a structure that's more than 99% empty space, yet it still holds together as a solid. Aerogel was first produced in 1931 by Samuel Kistler, who won a bet with a colleague that he could replace the liquid in a jelly without causing it to collapse. His method worked, and the result was unlike anything seen before. Despite the fragile, almost ghostly appearance, aerogel is surprisingly strong in certain ways. It can withstand many times its own weight and pressure. A piece of aerogel the size of a human hand can support a brick without breaking. And the material's unusual structure gives it a very low density, ranging from 0.001 to 0.5 grams per cubic centimeter, making some versions lighter than air itself. But one of its coolest properties is the insulating ability of it. Because it consists mostly of empty space, it is extremely resistant to heat transfer. In fact, it's one of the best thermal insulators that's known. NASA's used it extensively in space missions, including to capture comet particles in the Stardust mission, and to insulate Mars rovers against extreme temperature swings. But aerogel also has some unusual optical qualities. Some types are nearly transparent, while others do scatter light, giving them a distinctive bluish appearance. That effect comes from the way that the nanostructures within the material interact with light. It can appear almost unreal, like a piece of solidified fog that you can hold in your hand. But despite its strengths, aerogel does have limitations. It is brittle and it can shatter if handled roughly, though newer formulations have improved the toughness. Researchers have experimented with composites and hybrid aerogels to reduce the fragility while retaining the properties. This has opened the door to more practical applications, from insulating buildings and pipelines to use in personal protective equipment. The weirdness of aerogel lies in how it kind of defies our everyday understanding of solids. We expect solid objects to feel heavy, opaque, and dense. Aerogel looks fragile and weightless, but can insulate better than thick layers of traditional materials. It shows that material science can produce substances that don't behave at all like the materials we encounter in daily life. And while it's no longer a laboratory curiosity, aerogel remains one of the strangest materials, both in its appearance and its properties. Number 13. Metallic hydrogen. Metallic hydrogen, it is one of the rarest and strangest forms of matter ever studied. In its normal state, hydrogen is a simple gas, but under immense pressure, hydrogen can change into something radically different, a metallic solid that's believed to conduct electricity better than almost anything else. The idea for metallic hydrogen was first proposed in 1935 by physicist Eugene Wigner and Hillard Bell Huntington. They predicted that if hydrogen atoms were squeezed hard enough, their electrons would break free from their usual bonds and behave like the electrons in a metal, moving freely and carrying electrical current. For decades, this was purely theoretical because no lab could generate the pressures needed to make it happen. Those pressures are extreme. They're way beyond what's found on the Earth's surface. But metallic hydrogen is thought to exist naturally only deep inside giant planets like Jupiter and Saturn, where pressures in the core exceed millions of times the atmospheric pressure at sea level. In these environments, hydrogen may be compressed into a metallic form, and it may be responsible for the powerful magnetic fields of those planets. In the laboratory, producing metallic hydrogen has been a long-standing goal of high-pressure physics. In 2017, researchers at Harvard University reported that they had created a tiny sample by squeezing hydrogen between two diamond anvils at pressures of around 495 gigapascals. That's 5 million times the atmospheric pressure. However, the sample was minuscule, and the controversy remains over whether true metallic hydrogen was achieved, since it soon disappeared and couldn't be reproduced reliably. Other labs have attempted similar experiments, but the results are still debated. The reason it's so sought after, though, is that it may possess extraordinary properties. It's predicted to be a room temperature superconductor, meaning it could carry electricity with zero resistance without the need for extreme cooling. If that's true, it could revolutionize energy transmission, magnet technology, and even space travel. Superconductors are usually impractical because they require temperatures close to absolute zero, but metallic hydrogen could change all that. Another prediction is that metallic hydrogen might be metastable, meaning it could remain in metallic form even after the pressure is removed. So it could be produced once and then used in ordinary conditions. This would open up possibilities for incredibly powerful rocket fuels, since metallic hydrogen is expected to release enormous amounts of energy if it reverts back to its normal gaseous state. But what makes it so weird is that it challenges our understanding of materials at a fundamental level. Hydrogen is the simplest atom in the universe, and yet under extreme conditions, it may become the most exotic. While the exact details are still uncertain and much of the research is still ongoing, the very idea that the most abundant element in the cosmos can transform into a superconducting metal under pressure makes it one of the strangest known materials, even if stable samples on Earth have yet to be fully confirmed. Number 12. Self-healing concrete. Concrete. It's the most widely used building material in the world. It forms the backbone of modern cities and infrastructure. But ordinary concrete has a couple of major weaknesses. It cracks easily, and those cracks allow water and oxygen to seep in, leading to corrosion of the steel reinforcements and eventual failure of structures. To address this problem, scientists have developed one of the weirdest and most practical materials in recent years: self-healing concrete. The concept is simple, but it's kind of remarkable. Self-healing concrete contains these special additives, often bacteria or encapsulated compounds, that can repair cracks automatically when they form. One of the most promising approaches uses bacteria that produce limestone. These bacteria, like the Bacillus species, are mixed into the concrete in spore form, along with a nutrient source like calcium lactate. When the cracks form and water seeps in, the bacteria is activated. They consume the nutrients, multiply, and precipitate calcium carbonate, which fills the crack and restores the material's strength. Another approach uses microcapsules or vascular systems embedded in the concrete. When cracks open, capsules break and release healing agents like epoxies or other sealants. The material essentially patches itself without any humans. Well, the benefits of self-healing concrete are potentially enormous. Bridges, tunnels, dams, high-rise buildings, they could last decades longer without any costly repair. Maintenance budgets for infrastructure could be reduced and safety would be improved. For countries struggling with aging roads and bridges, like my state, this technology could make a major difference. The idea may sound futuristic, but it's already been demonstrated in real-world tests. Researchers in the Netherlands pioneered bacterial self-healing concrete, and pilot projects have shown that cracks up to a few millimeters wide can be closed within weeks. And in 2015, a Dutch company began selling self-healing concrete commercially, though the high cost has so far limited any widespread adoption. Traditionally, we think of concrete as static and lifeless. Once poured, it gradually degrades until it has to be repaired or replaced. But self-healing concrete behaves more like a biological system, actively responding to damage and repairing itself. This blurs the line between living and non-living materials in a way that is genuinely unusual. There are still challenges though. The long-term durability of the bacteria, the environmental impact of additives, and the scalability of the process are all areas of active study. But the principle has been proven, and as the costs come down, it could transform how we build and maintain the world. Number 11. Liquid metal. Liquid metal, also known as bulk metallic glass, is a family of alloys that combine the strength of metals with the unique structure of glass. Now, unlike ordinary metals, which have a crystalline atomic structure where atoms line up in orderly patterns, bulk metallic glass has an amorphous structure. This means its atoms are arranged randomly, more like a glass or a plastic than a traditional metal. The result is a material with properties that can seem almost contradictory. Ordinary metals are strong, but they tend to deform under stress through dislocations in the crystalline lattice. Glasses, on the other hand, resist deformation but are brittle and shatter when pushed beyond their limits. Liquid metal combines aspects of both. It can be stronger than steel, resist wear and corrosion, and still be molded with precision like plastic. This makes it unusual compared to conventional alloys. Liquid metal was first developed in the 1960s, but it was in the early 2000s that it began gaining attention when researchers at Caltech and companies like Liquid Metal Technologies explored its potential uses. Apple famously acquired rights to use liquid metal in its products, though so far it's only been used sparingly, for example in SIM card ejector tools. The weirdness of liquid metal is the remarkable mechanical properties it has. It's got high strength-to-weight ratio, meaning it can be extremely strong for its size. It's also highly elastic and can spring back to its original shape after deformation much better than ordinary metals. Traditional metals have to be machined, cast, or forged into shape, but liquid metal can be molded like plastic while retaining metallic properties. This means it can be cast into really complex shapes with smooth surfaces and fine details that would be difficult or expensive to achieve with ordinary alloys. Most bulk metallic glasses are made from alloys of zirconium, titanium, copper, and nickel. They require rapid cooling to prevent the formation of crystals during the solidification process. Now, this limits the size of parts that can be made, though advances in processing has allowed larger components in recent years. Applications would include medical devices, sporting goods, military equipment, and potential aerospace uses. The durability and smooth surface finish make it attractive for surgical tools and implants, while its strength is useful in high-performance sporting gear like golf clubs and tennis rackets. Aerospace engineers are interested in it for lightweight, durable components, though cost remains a barrier. Of course it does. Number 10. Superfluid helium. Helium is well known as the gas that's used in balloons, but under extreme conditions, it exhibits some of the strangest behavior of any substance. When cooled to temperatures near absolute zero, helium can become something known as a superfluid, a state of matter where it flows without viscosity. In this state, it behaves in ways that seem impossible for a liquid. Helium has two stable isotopes, helium-4 and helium-3, and both can become a superfluid, though at different temperatures. Helium-4 enters the superfluid state at about 2.1 degrees Kelvin, known as the lambda point. Helium-3 requires even colder temperatures below 0.0025 Kelvin, making it way harder to achieve. But what makes it so unusual is it can do things no ordinary liquid can do. It can climb the walls of a container and escape, forming a thin film that spreads out over any surface. It can flow through tiny pores that would block any normal fluid, and it also conducts heat with extreme efficiency, way better than copper or silver, because thermal energy is carried by waves in the superfluid. Well, superfluidity is a quantum mechanical phenomenon. At these low temperatures, the helium atoms lose much of their individual behavior and they start acting like a single quantum state. In helium-4, this arises from Bose-Einstein condensation. This is where a large fraction of atoms occupy the same quantum ground state. In helium-3, the mechanism is a bit more complex and involves the pairing of fermions in a way that's similar to superconductivity. The discovery of superfluid helium in the 1930s shocked the scientists that were working on it. Piotr Kapista, John Allen, and Don Meissner independently observed the phenomenon, and Kapista was awarded the Nobel Prize in Physics in 1978 for his work. Since then, superfluid helium has become a central tool in low-temperature physics, allowing scientists to study quantum phenomena on a macroscopic scale. Practical applications of superfluid helium are limited because maintaining the temperature so close to absolute zero is expensive and technologically challenging. However, it's invaluable in scientific research. The weirdness of superfluid helium lies in how completely it just defies our intuition about liquids. The idea of a fluid that can flow forever without slowing, climbing walls, and move against gravity sounds like something out of science fiction. Yet it's real and well documented. Superfluid helium is not a material that we use in everyday life, but it is one of the strangest and most fascinating states of matter known. Its discovery did expand our understanding of the physical world, and it continues to serve as a reminder that under extreme conditions, nature produces behaviors that seem almost impossible. Number 9. Graphene. Graphene. It's a single layer of carbon atoms arranged in a two-dimensional honeycomb lattice, and it's been hailed as one of the most remarkable materials ever discovered. While carbon is one of the most common elements on Earth, the arrangement of its atoms in graphene gives it the properties that seem almost too good to be true. It is incredibly strong, exceptionally light, and has unusual electronic characteristics that continue to surprise people. The material was first isolated in 2004 at the University of Manchester using a surprisingly simple method. They peeled layers of graphite, the material in pencil lead, using adhesive tape until they obtained sheets only 1 atom thick. Their work won them the Nobel Prize in Physics in 2010 and opened the door to a surge of research. Graphene is often described as the strongest known material. Its tensile strength is about 130 gigapascals. That's more than 100 times stronger than steel, despite only being 1 atom thick. It's also incredibly light. An area of graphene the size of a football field would weigh less than a gram. In addition to mechanical strength, graphene conducts electricity better than copper, which makes it attractive for electronics, energy storage, and engineering. The potential applications of it are vast. Researchers are studying graphene for use in flexible electronics, ultra-fast transistors, advanced batteries and supercapacitors, water filtration membranes, and even medical sensors. Still, though, there are challenges. Producing high-quality graphene at scale and integrating it into real-world products has proven difficult and expensive. Graphene's weirdness lies in how extreme and contradictory its properties are. It is simultaneously the thinnest material possible and yet one of the strongest. It's nearly invisible but impenetrable to gases, and it's a fantastic conductor of electricity and heat. Yet made from one of the simplest and most abundant elements in nature, these qualities push the boundaries of what we think materials can be. Number 8. Starlight. Starlight is a pretty interesting material and one of the most mysterious ever introduced to the public. Developed in the 1980s by Maurice Ward, a British hairdresser and amateur chemist, Starlight was said to have extraordinary heat-resistant properties. Demonstrations showed it withstanding intense flames and even the heat of a laser beam without burning or transmitting heat to the material underneath. It did seem to defy the limits of known materials, and yet its composition was never revealed, making it one of the strangest stories in modern material science. Ward claimed that Starlight could resist temperatures of up to 10,000 degrees Celsius, far higher than the melting point of most metals. In television appearances, he coated an egg with Starlight and held it in the flame of a blowtorch. After minutes of direct exposure, the egg remained uncooked, with only a thin char layer of Starlight on the outside. In other demonstrations, materials coated with Starlight showed little to no damage under the conditions that would normally vaporize steel. What made it so unusual was its origin. Maurice was not a trained scientist or an engineer, but an inventor working in his home workshop. He reportedly experimented with blends of polymers and ceramics until he arrived at the formula. Despite the attention it received, he never disclosed the exact composition, fearing it would be stolen or misused. He kept the formula secret until his death in 2011, and to this day, the exact recipe remains unknown. Skeptics have argued that Starlight may not have been as revolutionary as claimed, pointing out that independent verification was limited and that Ward often refused to let samples be taken for full analysis. Others counter that the televised demonstrations and official interest suggest that it was at least partially genuine. Without full disclosure, though, the truth remains uncertain. The tale of Starlight, it highlights how much secrecy and intellectual property can affect science. If Ward had shared the formula, it might have been developed further, tested more rigorously, and possibly put into widespread use. Instead, it remains a legend in material science, a material that may or may not have been as remarkable as claimed. Whether Starlight was a true breakthrough or an overhyped curiosity, it still remains one of the strangest materials ever reported, even if the world may never know exactly what it was made of. Moving on to number 7, Gallium. So gallium, it is a silvery metal that looks ordinary at first glance, but it behaves in ways that make it one of the strangest elements on the periodic table. Its most unusual property is its melting point, just under 30 degrees Celsius or about 86 degrees Fahrenheit. This means that gallium, a metal, can melt in the palm of your hand. Holding a solid piece for a few minutes transfers enough body heat to turn it into a liquid, a transformation that feels uncanny because we don't expect metal to behave this way. Gallium was discovered in 1875 by a French chemist whose name I'm going to butcher here, Paul-Émile Lecoq de Boisbaudran. Its name comes from Gallia, the Latin word for France. At the time, it was notable because its existence had been predicted a few years earlier by Dmitri Mendeleev, the creator of the periodic table, who left a gap for an element he called eka-aluminum. When gallium was isolated, it confirmed the predictive power of the periodic table. But besides its unusual melting point, gallium has some other peculiar characteristics. It remains liquid over a wide temperature range, from just above room temperature up to about 2200 degrees Celsius when it boils. That's a liquid range of more than 1800 degrees. It's way greater than that of almost any other element. Most metals melt and boil within a narrower span, but gallium stays liquid across conditions that would vaporize many materials. Gallium doesn't happen in pure form in nature, but it is usually extracted as a byproduct of aluminum and zinc processing. Despite being relatively rare in the Earth's crust, it is essential in modern technology. Gallium compounds are used in semiconductors, particularly gallium arsenide, which powers high-speed electronics, LEDs, solar cells, and laser diodes. Without gallium, many of the devices that underpin our modern communications and renewable energy would not exist. Another strange property is how gallium interacts with other metals. It can diffuse into the crystal structures of aluminum and weaken them, effectively causing aluminum to just crumble. This property makes gallium a laboratory curiosity, but also a reminder of how dangerous mixing certain elements can be for structural integrity. Gallium is not toxic in the way that mercury is, even though both are metals that can be liquid near room temperature. Because of this, gallium has been used for educational demonstrations to show the students the surprising behavior of materials. Watching a spoon made of gallium melt in a cup of warm water is a dramatic way to illustrate how unusual this element really is. Its weirdness lies in how it challenges our assumptions about metal. What we expect metals to be, solid, hard, strong at room temperature, gallium is, in contrast, soft enough to scratch with a fingernail and can melt from the warmth of your hand. This dual identity, strange, almost playful properties combined with serious industrial importance, makes gallium one of the weirdest known materials. Number 6. Transparent aluminum. Transparent aluminum? Aye, laddie. Well, this sounds like something out of science fiction, indeed from Star Trek, but it is real. More accurately known as aluminum oxynitride, or ALON. It's a ceramic material that is both transparent and incredibly strong. Its existence does seem to defy our usual categories of materials, since we think of metals like aluminum as opaque and reflective, while transparent materials are usually fragile like glass. ALON combines transparency with toughness, creating a material that feels too strange to be real. ALON is made from a mixture of aluminum, oxygen, and nitrogen. The result is a crystalline ceramic that can be polished into a clear glass-like form. Unlike ordinary glass, which is brittle and shatters, ALON is extremely strong and resistant to impact. It can withstand forces that would break or deform traditional glass, and it's often compared to sapphire in terms of hardness. The material was developed in the 1980s by Raytheon and has since been commercialized for military and industrial applications. Compared to traditional bullet-resistant glass, which is made of laminated layers that tends to be heavy and thick, ALON is lighter, thinner, and more durable. This makes it really attractive for use in armored vehicles, aircraft, and protective enclosures. ALON also has excellent optical properties. It transmits light from the ultraviolet through to the visible spectrum and well into the infrared, making it useful for sensors, cameras, and other devices that need to operate across multiple wavelengths. Producing ALON is complex and expensive, which has limited its widespread adoption. It requires some high-temperature processing and precision polishing to achieve the desired clarity and strength, but nevertheless, ongoing research aims to bring costs down and expand its use. As prices fall, it could be used in commercial products like smartphones, where a scratch-proof, shatter-resistant transparent surface is highly desirable. The weirdness of transparent aluminum comes not only from its unusual combination of properties, but also from the way it bridges the gap between science fiction and reality. This concept was popularized in the '86 movie Star Trek IV: The Voyage Home, where transparent aluminum was presented as a futuristic material. A few years later, real-world scientists produced ALON, which matched the fictional description almost perfectly. That coincidence captured the imagination of scientists and the public, turning ALON into a symbol of how science can sometimes catch up with fiction. Number 5. Magnetorestrictive Terfenol-D. So Terfenol-D, weird name, is a material that behaves in ways that seem kind of alien. It's an alloy made of terbium, dysprosium, and iron. And its most unusual property is magnetorestriction. This means that when a magnetic field is applied, the material changes shape, expanding or contracting in response to the field. The movement is tiny, usually only micrometers, but it is strong and consistent enough to be put into practical use. Terfenol-D was developed in the 1970s and 80s at the U.S. Naval Ordnance Laboratory. The name comes from its components: terbium, ferrum, the Latin word for iron, and nol for Naval Ordnance Laboratory, with the D added for dysprosium. The alloy was created in search of materials that could convert energy efficiently between magnetic and mechanical forms, and what researchers found was a substance that could respond to magnetic fields in ways that no ordinary metal could. This property has made it valuable for a surprising range of technologies. In sonar systems, for example, Terfenol-D can act as a transducer, turning electrical signals into sound waves underwater and vice versa. The material is also used in actuators, sensors, and vibration control systems. Because of the ability to move quickly and repeatedly without wearing out, it makes it ideal for precision engineering applications. Despite its usefulness, though, it's not widely known outside specialized industries. Rare earth elements it contains, terbium and dysprosium, are expensive and relatively scarce, which limits its production. But nevertheless, research into this kind of material continues, with Terfenol-D remaining the most prominent example. Watching a piece of metal physically change shape in response to magnetism kind of challenges our intuition about what metal should do. That makes it not only useful, but also one of the weirdest materials discovered in the last century. Number 4. Amorphous metallic glass foam. Metallic foams are materials that combine the properties of metals with the structure of a sponge. They're lightweight, full of pores, yet retain the strength and durability of metal. Among them, metallic glass foams are some of the strangest. These are materials that take bulk metallic glass, already unusual because of its amorphous atomic structure, and form it into porous foam-like structures. The result is a material that looks and feels completely different from what we expect of metal. Because the foam contains so many empty spaces, it's way lighter than a solid block of the same material. Yet because metallic glass is already stronger than many steels, the foam retains remarkable toughness. When compressed, the pores collapse in a controlled way, allowing the material to absorb large amounts of energy without breaking. That property alone has drawn interest for use in impact protection and shock absorption. For example, metallic glass foams could be used in vehicle crash structures, helmets, or even protective gear. They can dissipate energy from an impact more effectively than traditional foams or metals, which makes them ideal for safety applications. Scientists have experimented with blowing gas into molten alloys to create bubbles, much like foaming sugar to make candy and then cooling it rapidly to preserve the amorphous structure. The result is a metal that's strong but lightweight, porous but solid. Because these metallic glass foams are new and really expensive to produce, they've not yet been widely adopted. Most research remains at the experimental stage, with prototypes being tested for specific uses. They could reduce the weight of vehicles and aircraft while improving safety, or serve as innovative medical implants, where strength and lightness are both required. Metals are supposed to be dense, heavy, and rigid. A foam made of metal that you can easily lift in one hand, yet strong enough to withstand crushing forces, feels contradictory. Combined with an already unusual property of metallic glass, the foam version is doubly weird. Number 3. Teflon. The controversial Teflon. It is one of the strangest and most widely used materials in the modern world. Known chemically as polytetrafluoroethylene, or PTFE, it's a synthetic fluoropolymer that stands out for its properties. It's remarkably slippery, chemically resistant, and thermally stable. While today it's best known for its role in nonstick cookware, its story begins with an accident in a lab and has since extended to applications in aerospace, medicine, electronics, and countless industries. The discovery happened in 1938 when Roy Plunkett, a chemist working for DuPont, was experimenting with refrigerants. He had stored tetrafluoroethylene gas in pressurized cylinders, expecting to use it for further reactions. When he opened one of the cylinders, nothing came out. Curious, he cut the cylinder open and found that the gas had polymerized spontaneously into a white, waxy solid. At first, it looked unremarkable, but when Plunkett and his colleagues tested it, they realized they had stumbled upon something extraordinary. The substance resisted acids and solvents, didn't absorb water, and had a surface so slick that almost nothing could adhere to it. Instead of discarding it as a curiosity, DuPont began studying it, eventually commercializing it under the brand name of Teflon. Now, what makes it unusual is the molecular structure. It's made of long chains of carbon atoms, just like many other polymers, but every carbon atom is surrounded by a fluorine atom. This carbon-fluorine bond is one of the strongest in chemistry, which means the chain is extremely stable and resistant to breaking. The fluorine atoms also create a dense, shield-like layer around the carbon backbone, which makes it incredibly difficult for other molecules to get close enough to react. This gives PTFE its legendary chemical inertness. It doesn't corrode, doesn't dissolve, and it resists almost every chemical reagent known, including aggressive acids like hydrofluoric acid and concentrated sulfuric acid. Teflon's slipperiness is another property that sets it apart. On a microscopic level, surfaces have irregularities that create friction when objects slide across them. PTFE's fluorine coating is so uniform and unreactive that there's almost no attraction between it and other substances. The result is an extremely low coefficient of friction, measured to be as low as 0.05, making it one of the most non-stick surfaces in existence. In machinery, PTFE is used as a lubricant or bearing material, reducing wear and energy loss. In cables and wires, the smoothness allows conductors to be pulled through conduits without snagging. Even in space, Teflon has been used in mechanisms where ordinary lubricants would freeze or evaporate. One of the strangest aspects of Teflon is how it interacts with electricity. It is an outstanding electrical insulator, which means it doesn't conduct current even under high voltage. For this reason, it's been used extensively as coating on wires and cables, particularly in environments where safety and reliability are paramount. PTFE-coated wiring was used in aircraft, spacecraft, and high-performance electronics. But despite the controversies, the practical importance is undeniable. In the aerospace sector, it's been used in spacecraft like Apollo missions, where reliability was essential. In the military, PTFE-coated fabrics have been developed for protective clothing that resists chemicals. In industries, pipes and tanks lined with Teflon resist corrosion from aggressive chemicals. The material even appears in sports equipment, where its low friction helps skis and snowboards glide more smoothly, and in optics, where it reduces reflection and contamination. Just don't use it to cook your food. Number 2. Lutetium aluminum garnet, LuAG crystals. Among the many unusual materials developed in the last century, few stand out as much as the synthetic crystals made from rare earth elements. And one of the strangest is lutetium aluminum garnet, known as LuAG. At first glance, LuAG doesn't look extraordinary. It's a clear, transparent crystal that can be grown in the lab, polished, and cut into shapes. Yet its properties make it one of the weirdest we know of. It's incredibly dense for a transparent crystal, unusually stable, highly efficient at converting energy, and indispensable in advanced lasers, radiation detectors, and even medical imaging. It's strange not because it behaves erratically, but because it combines traits that don't normally go together in a single solid. Lutetium itself is one of the least abundant rare earth elements, tucked away at the far end of the periodic table with an atomic number of 71. Despite being called a rare earth, lutetium is not an impossibly rare thing, but it is difficult to separate from other lanthanides, which makes it expensive and hard to produce in quantity. It's also one of the densest and heaviest of the lanthanides, which already sets it apart. When combined with aluminum oxide in a garnet crystal structure, lutetium takes on qualities that make the resulting LuAG crystal surprising and indispensable. The garnet structure is the key part of what makes LuAG unusual. Garnets are a group of silicate minerals that are naturally found as gemstones, but in materials science, garnet refers to a specific crystalline arrangement that can be reproduced with different chemical ingredients. Aluminum garnet is one of these, and by substituting in lutetium, scientists can create a synthetic garnet crystal that's not only transparent but extremely dense. Most crystals we think of are clear, like quartz, diamond, and sapphire, that aren't nearly as heavy. LuAG combines the optical clarity we associate with gems with a density more akin to a heavy metal. This kind of combination leads to very strange but useful properties. One of the most important is its efficiency as a scintillator. Scintillators are materials that emit light when struck by high-energy radiation, like X-rays or gamma rays. This property is crucial for detectors in medical imaging, nuclear physics, and security scanning. LuAG scintillators are particularly good because the crystal is both dense, meaning it stops more of the incoming radiation, and transparent, allowing the emitted light to escape and be detected. This makes it possible to build compact, efficient detectors that provide high-resolution images. For example, positron emission tomography, PET scanners, which track radioactive tracers inside the human body, rely on scintillators to convert gamma rays into light. LuAG crystals doped with cerium ions are used in some of the best PET detectors, producing sharper images with lower doses of radiation. The stability of LuAG is another aspect that makes it kinda weird. Many scintillators and laser crystals degrade under prolonged exposure to radiation or intense energy input. LuAG, however, is remarkably resistant to that kind of damage. The stability comes from the strength of the crystal lattice, where lutetium atoms occupy positions that balance the overall structure, and the result is a material that seems to shrug off conditions that would destroy lesser crystals. Despite its many uses, though, LuAG remains obscure outside scientific and technical circles, partly because lutetium is rare and expensive. High cost limits its widespread use, but in applications where performance is critical, like advanced medical imaging, the benefits outweigh the expense. Compared to other weird materials, LuAG may seem less dramatic at first. It doesn't melt in your hand like gallium, it doesn't look like a cloud like an aerogel, and it doesn't defy light like Vantablack. Its weirdness is subtler. It's rooted in the way it combines qualities that seem contradictory. The idea of a heavy crystal that looks clear, resists radiation, bends light strongly, and glows when struck by invisible rays is enough to place it among the strangest engineered materials in existence. It's not a material most people will ever hold or even see, but its presence is felt in hospitals, laboratories, and industries that rely on precision. Number 1. Amorphous ice. So yeah, when most people think of ice, they picture the familiar crystalline solid that forms in freezers, on lakes, or in winter storms. That ice has a regular ordered structure where water molecules line up in a repeating pattern. What makes amorphous ice so strange is that it breaks that rule completely. Instead of forming in a neat crystalline lattice, water molecules are arranged in a disordered, glass-like state. It's still solid water, but it looks and behaves nothing like the ice we know. Amorphous ice is not something you'll ever encounter on the surface of the Earth under normal conditions. Here, water freezes slowly enough that molecules always have time to arrange themselves into the familiar hexagonal crystal pattern. Amorphous ice only forms under unusual circumstances, typically when water is cooled so quickly that the molecules cannot align before they're locked in place. Scientists can make it in laboratories by rapidly cooling water vapor onto a very cold surface, often below -150 Celsius, or by compressing ordinary ice at low temperatures until its structure collapses into disorder. The real importance of it lies beyond Earth. In the vacuum of space, water vapor condenses so quickly and at such low temperatures that amorphous ice is thought to be the most common form of frozen water in the universe. Spacecraft and telescopes have detected it on comets, icy moons, and interstellar dust grains. Unlike crystalline ice, which reflects sunlight in distinct ways, amorphous ice absorbs light differently, giving astronomers clues about its presence on distant objects. Another strange aspect is how it relates to one of the biggest mysteries in physics, the behavior of water itself. Water is famous for its anomalies, why it expands when it freezes, why it has such a high heat capacity, and why it behaves differently from other similar molecules. Some scientists believe that studying amorphous ice could unlock some answers to those puzzles. In particular, the differences between low-density and high-density amorphous ice may hint that water has more than one liquid state, separated by a hidden critical point deep below its freezing temperature. If true, this would mean that water can exist not just as a liquid, solid, and gas, but as two fundamentally different types of liquid, an idea that does challenge long-held assumptions. Amorphous ice may look unremarkable, essentially a cloudy or glassy solid, but its weirdness lies in what it reveals about water. It shows that even the most familiar substance on Earth has hidden behaviors that only appear under extreme conditions. It challenges our understanding of the phases of matter. It explains features of icy worlds beyond Earth, and it may even hold clues to life's origins. For something as ordinary as frozen water, that is extraordinary.